Yeah, so today we're going to take molecular symmetry, the things that we've learned so far, assigning point groups to molecules, looking at the character table, the Mulliken notations for the symmetries of various vibrations and for molecular orbitals, and we're going to assign those symmetries and use them in the transition dipole moment. So if you think about what the transition dipole moment is it's three functions multiplied by each other. So you have initial wave function, you have a potential wave function, a final wave function where it might go, and then you have light. All three of those functions have symmetries that can be found in the character table. So we assign the symmetries of those functions, and then we use the last page on your character table notes called the direct product tables. And those direct product tables tell us what happens when we have a function that has B1 symmetry times a function that has B2 symmetry, or a function that's A2 times a B1. You know, all of these possible combinations are in those direct product tables. And then we'll see what happens at the end. If it's not top row, then that integral will be 0. So we're way down here at the direct product table. So we start with the Lewis dot structure. We get the geometry, which gives us the point group, which gives us the character table. And now today we're going to be using the direct product tables to determine the selection rules for our spectroscopy. So these direct product representations, we have lots of functions multiplied by other functions. And this really helps. You did just a simple transition dipole moment integral by hand in one dimension, and you did it with just direct absorption or emission of light, so just x. But in scattering, you have x squared. You had to use the integration by parts, right? If you do x squared, it's nested, so you have to do integration by parts of integration by parts, and then maybe even a third step of integration by parts. So you have to do this 3 times and then bring all those results back to the top. It gets really complicated, and that's still just one dimension. If you're doing this in 3 dimensions, it's ridiculous. So using the symmetry is really the only way for us to understand quickly how these selection rules work. Even in a molecule, you have the total wave function, which is shown up here, and even I'll draw on here. Shown here is the wave function, the total wave function, and it is the product of the electronic wave function, the vibrational wave function. J is the rotational quantum number, and so that's the rotational wave function. And then we have nuclear wave functions, which in most cases for a chemist is not relevant, except for NMR. So nuclear spin is involved in NMR, and so there's a nuclear wave function for NMR. If you get into gamma ray spectroscopy or radioactive transitions, then you get into the nuclear wave functions. But for the most part, we're in a ground state nuclear wave function, and all chemistry happens, and we don't even know that wave function is there. So you could come up with the total wave function and the symmetry of the total wave function by knowing the symmetries of all of these. The nice thing is I don't know of an example where the ground state wave function isn't totally symmetric. Okay, so it doesn't interfere, and so it's the excited states typically that are asymmetric. Then we have this direct product, and this is if we looked at the character table, it's just every character in a particular symmetry multiplied by the corresponding character in another symmetry, and then you get if you look at 1s and -1s and so on, you'll get a different row in that character table. So instead of doing all of that and figuring it out, the direct product tables have already figured it all out for us. So we can go to the direct product table and it will tell us every possible combination of each row times each other row. Okay. This is how it applies to spectroscopy. The intensity, as we've said, is proportional to the square of the transition dipole moment integral. And so then if we know the symmetries of those, we can tell when that integral is going to be 0. So the result of this is the important point. If the result of the direct product of those 3 functions does not contain the totally symmetric irreducible representation, that's the top row of the character table, then that integral is equal to 0. And we say that transition is forbidden by symmetry. Okay? So I really want to emphasize that. If the result of the direct product does not contain the totally symmetric irreducible representation for that particular point group, then the transition is forbidden by symmetry. So this is the whole point for the symmetry exercise. is trying to figure out how these functions, when multiplied by each other, behave symmetrically. And if you end up with the top row in that integral, you know that integral is going to be non-zero. It's going to have a predicted potential probability of happening. So if light hits the molecule, it can cause that jump to occur. If it doesn't hit that top row, if it's B1 or B2 or A2 in C2b, that's the second, third, and fourth rows, then that transition is going to be forbidden by symmetry. So we use the VSEPR shapes to get the point group, we find the symmetries of the wave functions, and then we use the symmetry of the spectroscopic interaction. So we need to focus on light, and light is X, Y, or Z polarized. Think about what light is. It's electromagnetic radiation, and we're talking about electric dipoles, so we're really using the electric field. But the electric field's oscillating, so it might oscillate up if it's Z polarized light, it's oscillating up and down, and the magnetic field is 90 degrees to that, and it's 90 degrees out of phase. So light is maximum electric field, maximum magnetic field. Negative electric field, you want to say north and south on the magnetic field, and it's south. And so it's positive, north, negative, south. And it's doing this. And it's going through space the whole time. Yeah. Okay. It looks like a cheerleader thing to me. I don't know. So that's the symmetry of light. And so we just narrow it down and say we're going to talk about Z polarized light, or X polarized light, or Y polarized light. And so we're going to pick 3 different possibilities in that character table, and we'll do 3 different symmetry operations. And so in the most, you'll have 3 calculations for every 2 possible quantum jumps. And so now if we do scattering, and I've added this to the notes, it may not be in your notes, but it's scattering. You may have to write a few extra little diagrams today. It's a 2-photon process. And so we can have an incident photon in the Z direction, hit the molecule, and exit in the Y direction. So hitting the molecule, interacting with the electron cloud, can leave the molecule in a different state and spit out a photon in the Y direction. So that would be XY in the character table. So you can look at that character table and find the XY row, and that would be one of the possible scattering events where light comes in polarized this way and leaves polarized that way. Okay, so all of the ones that are second order would be for scattering. Yes.
So would that look like a arrow going into the molecule and then another arrow coming out in on the axis?
Yeah, if you were to draw it on the coordinate system, well, you were talking about the polarization direction. So for it to be polarized in Z, it would come in somewhere in the XY plane. It could come in along the X-axis or come in along the Y. So you really don't know where it's coming from. You just know where the polarization of the electric field is.
Okay.
And so then when it leaves, it might have polarization in Y, but it could go anywhere in the XZ plane. So it could leave at Z, leave at Y, leave at some or X, and leave at some combination of that, but the electric field was in the Y direction when it left. So we know where the electric field vectors would be. That's really all we know.
And do we categorize it by where it leaves or the direction it left?
We have to use both, because the symmetry of the lower state wave function, the symmetry of the upper state wave function, and the symmetries of both photons are all in that integral. Yeah. And so then we'll use the direct product. So let's do some examples. Let's flash back to the particle in a box before we get to molecules. Okay. So we only have one axis, that's the x-axis, so our light has to be polarized on the x-axis. There are no other axes in this system. So Z doesn't exist, Y doesn't exist. That's why I like this system. It's simple. You just have X wave functions and X polarized light. We only have 2 symmetry elements, E, which is identity, did nothing to the system, and inversion. We can invert that axis. We can take positive X values and make them negative. And we can see that the wave functions are either positive under inversion or negative under inversion, even or odd. And so this is our CI character table. It only has those two symmetry operations here, E and I. And so we label those wave functions with their even and odd character. If we were to do the inversion let's just show an example. if we did the inversion on the ground state, the left side equals or looks just like the right side. And so that's going to be a +1 under inversion. It's as if that we invert it, and it's as if that wave function was multiplied by +1, because it's the same. But if we invert this second state, we see it looks just like, if we flip that wave function, it looks like the wave function was then multiplied by -1, because the positives and negatives have switched if we were to invert that wave function around 0. Any questions about that? Because I'm using words, but if you're not picking up on what I'm saying, raise your hand. I know that there's more than one. Okay, you with me? All right. So then we had labeled our functions even and odd all the way up, but we used these terms in the character table, AU and AG. It's important to label them with those rows because the direct product table uses those rows. And so we set this transition dipole moment integral up from n to n prime with x in the middle. X is representing light. And so we find the symmetries of those. Let's look at the transition from n equals 1 to n equals 2. So we can easily find the symmetries of those. We'll just pick this case here, from 1 to 2. So what's the symmetry of state 1? That's going to be even, AG. State 2 is odd, AU. And light, up here in the character table, right here, X in the character table goes right here in the middle. So that's where that middle AU came from. And that middle one's always going to represent light. We have initial state, final state, and light in the middle. And it really doesn't matter if you get the initial and final mixed up. Okay, so just so you know, because you always want to know, is this important? No, it really doesn't matter which is which. It's just tradition. They first did this work on emission. And so the first one was the, this one here was the upper state and lower state, and it was emission. So it was going from higher or upper level to lower level. And then we just keep it for absorption using that same thing. So absorption is from 1 to 2, emission would be from 2 to 1. And you could switch those, it wouldn't really matter. But by convention, this is how it's done. And so now we need the direct product table to figure out these multiplications, because these little multiplication symbols are direct products. So we use this direct product table, and you can see that on the last page of your handout. If you want to find that one for CI, I think it's in there.
Yeah.
Right here. So it's up in the upper left corner. It's the second one down. Okay? I've got it on the board, but it's nice for you to see in the handout what we're talking about. Okay? And so we have this, I've drawn this little bracket here because we do them pairwise. We look at AU and we look at AG, and we find that in the table. Now they're lazy. This could be an AU as well, but they just print the upper triangle in these things. So, I don't know, they're saving ink. Whoop-de-doo, it would have cost another, fraction of a penny to print the rest of the table, but it's symmetric. So if you go here and you say AG times AU, it's blank. Well, they just swap it. It's AU and AG. Just find the intersection of those two, and this is the one that you want, AU times AG, so that one goes right here. So that they've been reduced by 1. So AU times AG is now AU. Everybody follow that? Okay. Then you do this one again. So you come down and you find AU times AU. So you come to your direct product table and you find the intersection of AU times AU, and you get the result AG. So that's the next one. And now I'm down to just one symbol, and it's inside the integral. Remember, this Dirac notation means we're integrating this function over all space, and then we're squaring it. Okay, but the integral part is what I'm interested in, and it's AG, which is the top row of my character table. So my end result as the symmetry of the top row of my character table, so that's not going to be equal to 0. That integral will have a result, and therefore, that's the 3 dots, therefore 1 to 2 is allowed. And so you're thinking, we got to do this for every one of these possibilities, 1 to 2, 2 to 3, 3 to 4. 1 to 4, 1 to 2. Yes, you could do it that way, or you could just look at the symmetries and say, you know, AG to any AU would be allowed, right? Because the symmetry is going to be the same. Whether I'm going to level 2 or level 4, I'm jumping to an AU. And so AG to AU is going to be allowed no matter what the quantum jump. So we're able to generalize. So can we generalize? Yes. If all AG to AU are allowed, then all AU to AGs are also allowed. And so if we look at this, we could have, you know, AG to any one of these AUs, and that's going to be allowed. But if we go from AU to AG, all we're doing is just swapping those two symmetries, and those would be allowed as well. And so we also have this possibility, AU to AG and AG to AU. So those are all three of the delta n equals 1s in this diagram, and one of the delta n equals 3s. But we know how this works. It's going to be 3, 5, 7. All of the odd number jumps are going to be allowed. And the evens, AG to AG, let's check that one out. See, so we just showed that all the others are allowed, but this one here is going to be AG to AG, and that's not going to be allowed. Let's see, do I show that on this one? Yeah, no. Let's do that one on the board really quickly. So. Okay, and I'll go full camera. All right. So this is the question. Can you see that? It's not great. It's better? Okay. So this is the question. Can we go AG to AG? So let's set this up. AG up here, AG here, and then X polarized light goes in the middle. That's going to be AU always in this character table. For C2V molecule, X is on that row for AU. So AU times AG from the direct product table is AU, and AU times AG is AU. So that is not top row. And so it's forbidden. This integral is going to be 0, and I don't even have to do it. And I love that. Okay. So I didn't like calculus till PChem, but that doesn't mean I like it enough to just want to do it all the time. Okay. So I really didn't like it when I was taking calculus. When I got to PChem, I was like, oh, wow, this is useful stuff. Yeah, so sorry for the mathematicians out there. So now let's talk about scattering, because it makes it a little more interesting. Okay, we're going to change things up a little bit. Let's talk about what a scattering transition is. There's certain things about scattering that you need to know. Okay, scattering is a 2-photon process. In our particle in a box, that has to be x squared. There is no xy. There's no xz. In water, there would be. I think earlier I said something about C2V character table, and I totally screwed it up. It should have been Ci. So when I was talking about in this molecule C2V, don't be confused. I screwed that up. Okay, it's the Ci character table. Okay, so in the Ci character table, x squared is on top row. Okay, and scattering is not absorption. Scattering is not emission. Okay, scattering is scattering. It's just like billiard balls, to use a photon concept. So a ball hits the molecule and bounces off. But when it's interacting with that molecule, some things can happen, okay? It can have a change of direction. In fact, that's really the only way you know if scattering has happened, is that light comes off at a different angle, okay? So that would be Rayleigh scattering. No change in the energy of light. But you could also have inelastic scattering. So the light hits the molecule and comes off with less energy. Where do you think the energy went? It went into the molecule. you know? And so now the molecule is shaking or vibrating or doing something at a higher energy quantum state, and light is left with less energy. Okay, so that would be inelastic scattering. So there's two types of scattering, elastic and inelastic. And what other possibilities are there? It either comes out with the same energy or less. Actually, it can't come out with more. It's still inelastic. What if the molecule that it hits is really excited and a light comes in, bam, and then it calms down? Where do you think that calming energy went? Into the light, the photon. So this photon comes in and hits the molecule. Pow! And it's got more energy and it's blue now. It's blue shifted. So that could happen, but you have to have excited molecules to do that. It's pretty rare because we don't just have molecules that are super excited all the time. But in like jet exhaust, you do. And so they'll use this blue shifted scattering to monitor, the combustion in like a jet engine. And they'll look at small molecules and they'll send lasers through there and they'll look at scattering events where the photons are given more energy by de-exciting the molecules. So that's pretty neat. So the Combustion Research Lab uses that a lot. So can light scatter inelastically in our particle in a box system and take a molecule or take our little particle from level 1 to level 2? Right? It could absorb light and go from level 1 to 2. Can it scatter light and keep some of the energy and end up in level 2? So look at that. That's the scattering phenomenon. Incident light hits it and is scattered off. Notice that the light is between energy levels. That's another important thing. We call this little dashed line, some call it a virtual state. It's not an energy state of the molecule. If there was an energy state, then light could be absorbed, right? Potentially. And so scattered light is not on one of the absorption peaks. It's somewhere else. So that's what's happening to all the light that's hitting things that's not absorbed. Okay? It's scattered off and reflected or whatever. So the incoming light hits our particle in a box. Can this happen? Can it spit out a photon and leave the molecule or electron in N equals 2? So we have state 1 here. We have state 2 here. And we have x squared in the middle. Now this would be a really long integral. It would require 2 or 3 integrations by parts, but it's very simple with direct products. State 1 is Ag, x squared now, up here. I'll do this on the pen so people can see when they look at the video later. So x squared here is Ag. And then this N equals 2 state is Au. Okay. And so this problem, even though it's a different phenomenon, looks the same in terms of symmetry, right? And so we use the direct product table. Ag times Ag is Ag. Not a problem there. And then Ag times Au is Au. So therefore, this integral is equal to 0, and inelastic scattering from 1 to 2 is not allowed. So you're not going to have a scattering event and have the molecule jump one level. So we could perhaps do it a different way. What scattering is allowed? So looking at if the final state, if you look back at this, what is the thing that poisoned this whole symmetry thing? Right? It was the fact that this upper state was Au. That's what poisoned the soup. If that upper state is Ag, then this would have been allowed. So it could make a molecule jump, or this electron jump from 1 to 3, have a delta N equals 2. And so all of the delta N's of 2, 4, 6, and 8 might be allowed. So let's verify that. So if the upper state is Ag, then we end up with an integral that's non-zero. And so what conditions are that? So the 1D particle in a box scattering selection rules are 2, 4, 6, 8, and so on, but also 0. Notice the ground state is Ag, and if light hit it and it interacted with light but spit the same energy photon back out, it's back at Ag. And so 0 is allowed, and that's Rayleigh scattering. So that's elastic scattering. And the 2, 4, 6, 8, etc. is Raman scattering or inelastic scattering. So these are two new terms for you. Rayleigh scattering, where it's elastic, there's no change in the energy of the photon. So you should write that down, because we're going to use that through the whole course. So Rayleigh scattering, no change in the frequency of light or the wavelength of that light. There is a change in direction, so it hits it and changes direction in some way. You said, well, isn't there a possibility it could emit it in the same direction? Yeah, it would have just slowed down. You couldn't tell that it had done anything. And so light that just slows down, we call that the refractive index of the material it's going through. Yes.
Does Rayleigh only occur at that ground state level, or can it occur?
It can occur, like if a molecule is excited in level 3, say, then it could be Rayleigh scattered back to level 3. Yeah.
So
Good
as
question.
long as it goes back to where it started.
Yes, that's Rayleigh scattering, and that's elastic scattering. So those are the same, they mean the same thing. Elastic scattering actually is probably a better term because it means something, right? Elastic means something to me. Rayleigh doesn't. That's just some dude's name, okay? But the elastic scattering is the content, the informational content. Raman scattering, it's Raman, not ramen, not the noodles. Okay, so it's and it's inelastic scattering. So there's been a change to the energy state of the molecule and a corresponding change to the energy state of the photon of light. So this would be Raman scattering. You see that little arrow up here? So the incident light comes up to this virtual level. It's not going to interact with any of the energy levels of the molecule or atom. And then this yellow, or it's called a red-shifted photon in this case. Green light comes in and yellow light comes out. It's a longer wavelength, a lower frequency. And so that would be the Raman effect. So you can take a molecule from 1 and pump it up to level 3. Pump it up to level 3 with this inelastic scattering. And we actually can do that too with lasers. We can pump a substantial amount of molecules up into these other upper layers, upper levels. So let's do one with the molecular orbitals. Okay. So here we have ammonia, and we have the highest occupied molecular orbital. So you remember those terms from organic, the HOMO to LUMO transition? Here's some pictures of one. So this is a picture of the highest occupied molecular orbital. So this is the highest orbital in ammonia that has 2 electrons in it. And then the next orbital is the lowest unoccupied molecular orbital. So here's the next orbital in the MO diagram for ammonia, but there are no electrons in it. It's waiting. It's there theoretically. And then can an electron be promoted to that orbital using light? Well, now we're in 3 dimensions. Okay, so can this transition occur? Well, since we're in 3 dimensions, we have X, Y, and Z polarized light. But this system has threefold symmetry. So X and Y are really the same. You can't tell the difference between the X direction and the Y direction in a threefold, a fourfold, anything with symmetry of 3 or greater. We call that a symmetric top. And X and Y behave the same. They're coupled. How do I know they're coupled? Look at the character table, and you'll see X and Y are connected to each other. They're in parentheses. So this means that the X direction and the Y direction are they have the same properties. What kind of properties would be the same? Well, moment of inertia would be one. So if I have something with threefold symmetry, like a equilateral triangle, if I flip it like a dinner plate, okay, it has the same moment of inertia around the x-axis as it does around the y-axis. And that seems odd for a triangle. You might think there was a way to turn it where x would be different than y. But threefold, fourfold, fivefold symmetry, those are symmetric objects, and they have the same moment of inertia around x and y. Same kind of thing in the electron cloud. X and y behave the same way in a symmetric top, something with threefold symmetry. So we just really have to do 2 problems. We have to do one for Z and one for XY light. So to set the problems up, we have the LUMO, the HOMO, and light in the middle. And so does this transition dipole moment integral equal 0? Here's for Z polarized light. We go to the character table and we see Z. It's A1, so we have A1 in the middle. We were given the symmetries of our HOMO and LUMO, so this was given to you here and here. Now, this one up here, I'm not sure that I wouldn't ask you this one on a test, but this one I would. So you need to look at that one. Those are my glasses. Okay. You need to look at that that orbital and see if you could assign the symmetry of that molecular orbital. You should be able to. Okay, just look where the cloud's sloshing. It's sloshing up and down on the z-axis. Yeah, yeah. This one up here is sloshing kind of in a circle. Okay, it's more like a breathing mode. In the middle is a little red zone, and it's getting thinner, and the outside's growing. And so this cloud's growing in x squared, y squared. It's like a circle that's getting bigger and smaller. And so you would find x squared, y squared in the character table and see that that's A1. So the LUMO is really x squared, y squared. It's a puffy cloud, like growing like a donut, bigger and smaller. Okay. But I would definitely feel comfortable giving you this lower one on an exam. Word to the wise. Okay. So let's do these direct products. So here's the direct product table for C3V. Go find that in your notes if you can. Yeah, perfect. Notice that this is the same direct product table for D3, D3D, and D3H. Okay, so again, they're saving ink. If it's the same table, why print it 4 times? So they just put all those point groups up at the top. So if you see C3V in there and you see all those other D groups, you're like, ooh, do I have the right one? Yeah. If you're looking for C3V, just find it in that table. And once you find it, you've got the right table. Okay? And so this is pretty straightforward. We have E times A1. So we come up here and we find E times A1. So the first pairing is there. And let's do the Z polarized light. The animation is a little out of order. So we have A1 times A1 times A1. So what are we going to do with that? I mean, anything times A1 is itself, if you notice that. So A2 times A1 is itself, and E times A1 is itself. Well, A1 times A1 is constantly going to give A1. And so this one is going to equal A1, therefore non-zero. So Z-polarized light is allowed, not a problem. But what about XY? We come over here, E times A1 gives E, and then E times A1 again gives E. Not the top row. So even in 3 dimensions, it's just as simple as it was in 1 dimension. We do 2 of these direct products, and we look at the character table. And we've done an ungodly integral. You think of this HOMO and LUMO and the Cartesian coordinates and that function, that would be a mess. I don't want any part of it, but I can look at the symmetry and tell you right now that X and Y light coming into this molecule cannot excite the HOMO to LUMO transition, but Z light can. And so the direct product is E, so the transition dipole moment is 0 for XY polarized light, but the HOMO to LUMO transition is allowed for Z polarized light. So this is why I like symmetry. We learn it in 1 dimension, and then we can bridge over to 3 dimensions using symmetry and just have an intuition as to how the molecule is going to behave with light. There's some more examples here in the notes that you can work through. Here's one for rotational levels. So rotational energy levels for water, I think this is, they also alternate A1, B1, etc. So this is rotation around Y in water, and that's shown to the right here. So look down here, this is RY in water. Where'd that come from? Well, look down here, RY is B1 in the character table for water. So we're rotating around the y-axis. Can this rotational mode be excited by direct absorption of light? We have the C2V character table. We find that rotation. It's B1. And so then the ground state is going to be A1 because it alternates. A1, B1, A1, B1. So we're going from A1 to B1, and we're using light. So we have our light is Z, X, and Y. And so we can try it with Z. We have Z here, that's A1. We had our ground state, which is A1, and we had rotation around Y, which is B1. So A1 times A1 is A1, and then A1 times B1 is B1. So Z polarized light cannot cause this rotation. Okay. X polarized light. So X is B1, that's down here. A1 times B1 is B1, and B1 times B1 is A1. So yes, X polarized light can cause rotation around Y. And so we can look at these rotations and see that if we're starting in a top row state, an A1 state, and RY is our upper state, X is going to be B1 as well. Those are kind of compatible, right? And so that's going to make it allowed. What about RX? If RX is B2, Y polarized light is B2, and those are compatible. So they'll cancel out. So you can kind of, once you get familiar with this, and you may not be familiar enough at this point to do that, but once you get familiar enough with this, you could look at this character table and see, yeah, X polarized light will excite rotation around Y, and Y polarized light will excite rotation around X. But nothing can excite rotation around Z. Okay? Because there's no polarized light on that row. And so rotation around Z is just not something that can interact with light. Now, it can interact with 2 photons of light. So in the XY polarized situation, that would work out. So a photon coming in on the x-axis and leaving on the y-axis could leave the molecule in an excited rotational state around Z. So that's why this character table is so useful. You can just sort of look at the experiments that you can do for the different molecules. Vibrational levels, we could do the asymmetric stretch. I just want to leave these in the notes for you so you could look at other examples and work your way through them. Okay? So here's the key. You can certainly do these kinds of problems with extra explanation in your pages. Don't just copy this page. That's not gonna count. But if you go in and you say, okay, here's where I got this number from the character table, and I got this from the direct product table, and so on, there's some extra examples in the notes for you. Last minute for questions. Now, I know people say, oh, I don't want to ask you a question because then people will groan and everything like that. But to heck with them, okay? This is your grade. So what's confusing you at this point? Speak up. Yes?
So whenever we're finding the asymmetric and symmetric stretches,
Yes.
the Mulliken notation using the vector cancellation, for C2B, it's going to be different from C3B.
Yes, yes. And so you'll look at those molecules and you'll compare them to the axes, and then look at that character table for that point group. That's why if you get the point group wrong, you totally screwed everything up because you got the wrong character table. If you get the coordinate system wrong, even if you have the right character table and the right point group, if you get the coordinate system wrong, you've screwed it up. So even though symmetry is easy, there's still a lot of things that you got to keep in check. Okay. In fact, Dirac, one of the most brilliant mathematicians, an interviewer asked him, "Is there anybody that you just don't get?" Right? Because this is a brilliant man, and he was curious. As a historian, he's like, "Is there any scientist out there that you just don't get?" And Dirac said, "Hermann Weyl." Hermann Weyl invented this symmetry stuff. And so Dirac could do the calculus all day long, but the symmetry stuff he never really studied. I wish he'd had my class. No, I'm joking. A little bold statement there.